Transfusion is a novel multimodal model that integrates both discrete and continuous data, enabling the generation of text and images in a single transformer. This model combines the language modeling loss function, next token prediction, with diffusion to train on mixed modality sequences. Unlike traditional approaches, transfusion does not require quantizing images or using separate models for different modalities, thereby maintaining the integrity of the data. The transfusion model utilizes standard embedding layers for text tokens and patchification layers for images, which are processed using causal attention for text and bidirectional attention for images. A decoding algorithm has been developed that combines the standard practices of text generation from language models and image generation from diffusion models. In comparison to the chameleon approach, transfusion models scale better in every combination of modalities. In text-to-image generation, transfusion achieves better fit and clip scores than chameleon at less than a third of the compute. Similarly, in image-to-text generation, transfusion matches chameleon at 21.8% of the flops. Surprisingly, transfusion is also more efficient at learning text-to-text prediction, achieving perplexity parity on text tasks around 50% to 60% of chameleon's flops. Ablation experiments reveal critical components and potential improvements for transfusion. Intra-image bidirectional attention is essential, and replacing it with causal attention negatively impacts text-to-image generation. Adding U-net down and up blocks to encode and decode images allows transfusion to compress larger image patches with minimal loss to performance, potentially decreasing the serving costs by up to 64 times. Transfusion can generate images at similar quality to other diffusion models. A 7B transformer enhanced with U-net down, up layers, 0.27B parameters, was trained from scratch over 2 T tokens. 1 T text tokens and approximately 5 epochs of 692 M images and their captions, amounting to another 1 T patches, tokens. This model outperforms popular models such as DALL-E2 and SDXL on the Gen-Eval benchmark. Unlike those image generation models, it can generate text, reaching the same level of performance as Llama 1 on text benchmarks. These experiments demonstrate that transfusion is a promising approach for training truly multimodal models. Transfusion combines the language modeling loss function with diffusion to train a single transformer over mixed modality sequences. This model can perceive, process, and produce data of every modality, making it a powerful tool for various applications. The paper discusses the concept of diffusion models, specifically denoising diffusion probabilistic models, DDPM, which operate on the principle of learning to reverse a gradual noise addition process. These models are suited for tasks involving continuous data like images. The forward process defines how the original data is turned into noise, while the reverse process of denoising is what the model learns to perform. In the context of image generation, early diffusion models worked directly in pixel space but proved computationally expensive. Variational autoencoders, VAEs, can save compute by encoding images into a lower dimensional latent space, allowing downstream models like latent diffusion models, LDMs, to operate efficiently on compact image patch embeddings. For autoregressive language modeling approaches, images must be discretized, achieved through discrete autoencoders such as vector quantized VAEs, VQVAEs, which introduce a quantization layer that maps continuous latent embeddings to discrete tokens. The paper also presents the transfusion model, which combines the capabilities of language models and diffusion models. It uses a pre-trained language model to generate text tokens that are then used as input to a diffusion model for image generation. This allows for high-quality image synthesis conditioned on textual descriptions. The model is trained using a combination of language modeling and denoising objectives, with the latter being the same as in standard diffusion models. The paper demonstrates the effectiveness of the transfusion model in generating diverse, high-quality images based on textual prompts, outperforming existing text-to-image models. The transfusion model's architecture consists of a pre-trained language model that is used to generate a sequence of text tokens from the input prompt. These tokens are then used as input to a diffusion model, which generates an image. The model is trained using a combination of language modeling and denoising objectives, with the latter being the same as in standard diffusion models. The paper demonstrates the effectiveness of the transfusion model in generating diverse, high-quality images based on textual prompts, outperforming existing text-to-image models. The research discusses a novel method called transfusion, which enables training a single unified model to understand and generate both discrete text and continuous images. The model's architecture primarily consists of a transformer, processing sequences of high-dimensional vectors. For text, it uses lightweight modality-specific components, such as embedding matrices, while for images, it experiments with simple linear layers and U-net-down blocks. The transfusion method combines causal and bidirectional attention patterns, allowing every image patch to attend to every other patch within the same image and to text or patches of other images that appeared previously. This architecture is trained using a combination of language modeling and diffusion objectives, which are added with a balancing coefficient. The training objective is reflected in the decoding algorithm, which switches between LM and diffusion modes. The model is evaluated on various benchmarks, including text-to-text and text-to-image tasks, demonstrating its viability and scalability. The paper presents a novel approach to multimodal generation, introducing transfusion, a model that uses continuous image representations and diffusion-based image synthesis. It provides an overview of the evaluation suite, including metrics such as perplexity, accuracy, CIDR, and clip scores, as well as the Gen-eval score. The model configurations are detailed, with 5 different sizes ranging from 0.16b to 7b parameters, following the standard settings from Llama. Optimization techniques include random initialization, ADAM-W optimization, and a learning rate schedule. Inference methods are also described, including greedy decoding for text and CFG for image generation. A controlled comparison with Chameleon, a prominent open science method, reveals better scaling laws for transfusion in various benchmarks, including text and image generation tasks. This is demonstrated through logmetric over log flops curves and estimated relative compute efficiency, showing transfusion's superior performance in both text and image tasks. Ablation studies indicate that transfusion's improvements may stem from its ability to model text more efficiently due to the absence of competition between text and image tokens in the output distribution. The paper concludes by discussing the potential for further research into this phenomenon and the implications of transfusion's continuous image representations on multimodal generation. The research discusses the transfusion model's performance at different scales, showcasing its viability for multimodal modeling in a controlled environment. Page 9 presents the performance of transfusion and chameleon models at various scales, highlighting the transfusion model's efficiency in terms of flops needed to match chameleon's results. Page 10 delves into architecture ablations, specifically attention masking and patch size, demonstrating the benefits of intra-image bidirectional attention and the performance trade-offs with patch size. The use of U-net encoding is also found to be advantageous, particularly in tasks involving the image modality. These findings suggest that the transfusion model is a scalable and effective approach for multimodal modeling, with room for further improvements and extensions. In this research, the authors explore the use of U-net layers in a transformer-based image-text model, dubbed Transfusion, to enhance its performance on image generation and captioning tasks. The study compares different patch sizes for the U-net and linear variants of transfusion, showing that U-net layers consistently outperform linear patchification across various benchmarks. The authors also experiment with limiting the diffusion noise to a maximum of T equals 500, which significantly improves image captioning performance without affecting other benchmarks. The paper further compares the performance of a 7B parameter transfusion model with U-net encoding, decoding layers against state-of-the-art image generation models and text-generating models. This comparison demonstrates that transfusion achieves similar performance to high-performing image generation models, surpasses previously published models, and performs on par with the Llama models in text generation tasks. The study concludes that incorporating U-net layers into transformer-based models can lead to substantial improvements in image generation and captioning tasks, even when the model size is relatively small compared to other state-of-the-art models. Transfusion models, a novel approach to multimodal learning, aim to bridge the gap between discrete sequence modeling and continuous media generation. These models are trained on two objectives, tying each modality to its preferred objective, enabling the generation of any modality. Despite incurring little to no parameter sharing cost, transfusion models scale efficiently and demonstrate promising results in both text and image generation tasks. In the context of image editing, fine-tuning a 7B transfusion model with an 8K publicly available image editing dataset shows that it can adapt and generalize across new modality combinations. The edited images from this fine-tuned model, as shown in Figure 6, indicate that transfusion models can perform well in tasks such as changing the color of a cupcake on a plate or converting a tomato to a green olive. The paper also discusses related work, including Flamingo, which uses image patches as inputs for visual understanding, and Chameleon, which converts images to sequences of discretized tokens before training over combined text-image token sequences. However, these approaches are either restricted to input-level multimodal tasks or lag behind state-of-the-art models in continuous data generation. Furthermore, the paper highlights the application of diffusion models and their generalizations to discrete text generation, as seen in Li et al. 2022, and Gatt et al. 2024. This research direction may unlock new ways to fuse discrete and continuous modalities in a single model. The conclusion emphasizes the potential of transfusion models in exploring the surprising difficulty of natural yes/no questions, as demonstrated by Boole Q. Clark et al. 2019, and the improved baselines with momentum contrastive learning, Chen et al. 2020. The paper concludes by acknowledging helpful discussions and funding sources. The paper presents a comprehensive overview of the Llama 3 herd of models, a cutting-edge AI model that excels in various multimodal comprehension and creation tasks. It is designed to tackle complex reasoning challenges through its innovative architecture and training methods. This model surpasses previous models in tasks such as question answering, image generation, and multimodal question answering, demonstrating superior performance in both understanding and generating multimodal content. In addition, the authors discuss the development of a new method for high-resolution image synthesis using rectified flow transformers. This approach enables the creation of high-quality images with remarkable detail, outperforming existing techniques. The proposed model can generate images at resolutions up to 1024 by 1024 pixels, making it a significant advancement in the field of image generation. Furthermore, the paper introduces a novel technique called discrete flow matching, which aims to improve the efficiency and accuracy of multimodal reasoning tasks. This method leverages the concept of flow matching to enhance the alignment between different modalities, leading to better comprehension and generation capabilities. The research also highlights the importance of scaling rectified flow transformers for high-resolution image synthesis. By scaling up the model size and adjusting the training parameters, the authors achieve state-of-the-art results in generating high-quality images. This work contributes to the ongoing efforts in developing more powerful and efficient AI models. Overall, the paper presents a comprehensive exploration of various AI models and techniques aimed at enhancing multimodal comprehension and creation. The Llama 3 herd of models, rectified flow transformers, and discrete flow matching are all innovative solutions designed to push the boundaries of what AI can achieve in terms of understanding and generating complex content. The research paper discusses the advancements in text-to-image synthesis models, focusing on the use of diffusion models and their capabilities in generating high-resolution images from textual descriptions. It highlights the importance of understanding the limitations and potential improvements of these models, particularly in terms of resolution and visual fidelity. The authors emphasize the role of the CLIP model, which is a powerful text encoder that has shown promising results in text-to-image synthesis tasks. They also mention the development of the DALL-E model, which utilizes a hierarchical approach to generate images based on textual input. This hierarchical method allows for better control over the generated images and improves their quality. The paper further explores the concept of classifier-free guidance, a technique used to guide the diffusion process towards generating images that are more likely to match the input text. This method has been shown to significantly enhance the quality and relevance of generated images. In addition, the authors discuss the concept of flow matching, a technique designed to improve the performance of diffusion models by adjusting the flow of the diffusion process. This approach aims to reduce the likelihood of generating low-quality or irrelevant images during the synthesis process. The paper also touches upon the issue of evaluating the performance of text-to-image synthesis models, emphasizing the need for a more comprehensive evaluation framework that considers both visual fidelity and textual relevance. The authors propose the use of the Generative framework, which provides a more nuanced evaluation of generated images based on their alignment with the input text. Finally, the paper concludes by highlighting the potential future directions for improving text-to-image synthesis models, including the exploration of new architectures and training methods. It also emphasizes the importance of understanding the limitations of these models and addressing them to achieve higher quality and more realistic image generation. The referenced paper cites various studies on transformer models, image editing, and text-to-image generation. Notably, it mentions social IQA, which focuses on common-sense reasoning about social interactions, and Rhoformer, an enhanced transformer with rotary position embedding. The paper also cites Llama and Llama 2, open foundation language models, as well as neural discrete representation learning, which explores neural discrete representation learning. Additionally, it references CIDR, a consensus-based image description evaluation method, and HelloSwag, which examines whether a machine can finish a sentence. The paper's autoencoder details are presented, with the training objective for the VAE closely following that of Esser et al., 2021. The loss function combines L1 loss, perceptual loss based on LPIPS similarity, patch-based discriminator loss, perceptual loss based on internal features of the MoCo V2 model, and KL regularization term. The VQGAN's training objective is similar, with the exception of replacing the KL loss with the codebook commitment loss. The vector quantization layer is applied after projecting the encoder outputs to 8-dimensional space. The training setup for the VAE and VQVAE is the same, with the same amount of training compute, training data, and encoder-decoder architecture. The paper presents examples of images generated from a 7B transfusion model trained on 2T multimodal tokens, as shown in figures 7 and 8. Additionally, it showcases random examples of image editing by a fine-tuned 7B transfusion model in figure 9. The images generated by the 7B transfusion model, trained on 2T multimodal tokens, showcase a diverse range of creative and imaginative scenes. In figure 7, we see an array of unique images, including a sunrise in downtown Seattle with a car made out of vegetables, an espresso machine that makes coffee from human souls, intricate origami of a fox and a unicorn in a snowy forest, and a Rembrandt painting of a raccoon illuminated by a single beam of light. Other notable images include a psychedelic tree of life illuminating dust in a mystical cave, a photo of a person with the head of a cow wearing a tuxedo and black bow tie, and a filmed still of a cute anthropomorphic cheeseburger relaxing on the couch. In figure 8, the model continues to demonstrate its ability to generate varied and imaginative images. We observe a woman under a blanket, a horse reading a book, a light bulb containing a sailboat floating through the galaxy, and a monarch butterfly. The images also include an expressive oil painting of a chocolate chip cookie being dipped in milk, an angry duck doing heavy weightlifting at the gym, and an emoji of a baby panda wearing a red hat and green gloves. Additional scenes depict a tranquil, anime-style koi pond in a serene Japanese garden, a massive alien spaceship shaped like a pretzel, graffiti of a funny dog on a street wall, and a spacious, serene room influenced by modern Japanese aesthetics with a view of a cityscape outside the window. The final images feature a raccoon wearing a cowboy hat and black leather jacket behind a backyard window, a relaxed garlic with a blindfold reading a newspaper while floating in a pool of tomato soup, and a bear wearing a suit and top hat in a river in the middle of a forest, holding a sign that says, "I can't bear it." These images demonstrate the model's capability to generate diverse, creative, and often humorous scenes, showcasing its potential in the realm of multimodal token-based image generation. In the context of image manipulation and editing, a fine-tuned 7B transfusion model is utilized to alter various elements in an image. The model allows for changes such as changing the closest keyboard to be all black, transforming graffiti on a truck into calligraphy writing, adding mountains to the background, replacing an airplane with a Black Hawk helicopter, adding a blue rug to the floor, deleting overhead lights on top of the sink, changing a roll of thread into a roll of wire, and altering a baseball bat to be all brown. These modifications are demonstrated in Figure 9, showcasing the model's capabilities in editing images. The fine-tuned 7B transfusion model operates by leveraging advanced neural networks and machine learning algorithms that enable precise control over image content and style. This model is trained on large datasets of images and their corresponding attributes, allowing it to understand and manipulate different components within an image effectively. The model's architecture consists of multiple layers that process and transform the input image, enabling the desired edits to be applied efficiently. The process of fine-tuning the model involves adjusting its parameters to better fit the specific requirements of the task at hand. In this case, the model has been optimized for editing images based on user-specified instructions. The fine-tuning process requires careful selection of hyperparameters and training data to ensure that the model learns to accurately identify and modify the desired elements in the image. The use of such models has significant implications for various applications, including graphic design, digital art, and content creation. By enabling users to make precise edits to images, these models can streamline workflows and enhance creative possibilities. However, they also raise ethical concerns related to image manipulation and authenticity, highlighting the need for responsible use and appropriate safeguards. In conclusion, the fine-tuned 7B transfusion model demonstrates impressive capabilities in editing images according to user-defined specifications. Its technical underpinnings involve sophisticated neural networks and machine learning techniques, which are critical for achieving accurate and efficient image manipulation. As this technology continues to evolve, it is essential to consider both its potential benefits and challenges, particularly in terms of ethical implications and responsible use.